Greetings, everybody. We're going to talk about inverse functions today in Lesson 7 in our pre-calc class. And our objective, like it says, is to find inverses of functions. So first off, what are inverses? Well, let's take this function right here. F of x equals the coordinate points 2, 7, 8, -3, and -12, 0. This notation is really important. Do not read that as f to the -1 power. That represents f inverse of x. So when you see that, it means that f inverse of x is the point 7, 2, -3, 8, 0, 10. So let's check it out. How, in fact, are these different? If you said, well, basically the x and the y are switched, you've got the right idea here. An inverse is basically the result of switching your domain, your x, with your range y. Now, there are a few more things attached to it, but that's a good working definition to start with. So let's find an inverse. By definition, it says to switch f of x, to switch x with y. And you look here and you say, well, I see an x, but y? I don't see any y's. How am I supposed to switch x and y if there's no y's? Well, understand that when we say f of x, it's the same as saying y. So then to actually find your inverse now, you just switch this x and that y, and you get something like this. Then to finish, all we do is just solve for y. So first thing I'm going to do is move the 6. So I get x plus 6 equals 3y. After that, we divide by 3. And I get y equals x plus 6. Or you could say 1/3 x plus 2. You can say, well, how does that work out? It works out basically like this. I'm looking at x plus 6 over 3. Since there are multiple terms on the top, 2 terms on top, separated by a plus or a minus, and only 1 term on the bottom, I can separate them. And x divided by 3 is the same as saying 1/3 x. And hopefully you know that 6 divided by 3 is in fact 2. So that's where that answer came from. So that's kind of what's going on here. Now, we're not done in that. I don't want you to leave your answer as y. I want you to do this. Since we started off with f of x equaling, you know how you changed f of x to y? Well, now I'm going to change the y back to f inverse. Let's take a look at the graph on this. So what I've done is take some screenshots off of my calculator. So in y1, I put in the function 3x minus 6 for my f. And in y2, I put in the inverse that we found, x plus 6 over 3. And then I graphed both of them. Now, I want to take it one step further and see, is there any kind of graphical relationship between them? And I know some of you might say, well, they intersect, and not all inverses intersect, but you'll see. So I want to add in the parent function y equals x. Remember, passes through 0, 0, slope of 1, that guy. Let's add that into the mix here. And what do you see now? Well, hopefully you see that the line y equals x goes right down the middle between those two. For instance, here is your f of x. Here is your f inverse of x. It's not so much that it intersects them, it's that it does this. It is a line of symmetry. So if you have correctly drawn your function and its inverse, this line right here, this y equals x, should cut it into 2 equal halves. You should see the mirror reflection across that line y equals x, whether they intersect or not. I mean, I could have inverses that do this. I could have a function look like this, and please forgive my drawing, but they don't necessarily have to intersect. They just have to have that line y equals x serve as the line of symmetry for it. Okay, let's even take a look at the table on this. I think this is worth, taking a look at. Now again, y1 was f of x, y2 was f inverse. So hopefully you see that in the red right here, f contains the points 1, -3. F inverse, which is this one, contains the point -3, 1. So does it basically do what we said? Is it the result of switching x and y? 1, -3 becomes -3, 1. If you look even closer, 2, 0 becomes 0, 2. So yeah, that kind of makes me feel a little better about things. I would not consider this proof, like a mathematical proof of there being inverses, but it does shed a little light on, what it should look like on a table. So that's probably a bullet point at the bottom that's not, that is worth looking at. Okay, let's try a couple more here. Now, let me take a look at this one. So first thing I'm going to do is call this y equals 4x plus 9. I'm going to switch x with y, so it now becomes x equals 4y plus 9. Then I subtract 9 from both sides, so I get x minus 9 is 4y. With those canceling, I divide by 4, and I get x minus 9 over 4 is y. Again, we started with f of x, so I'm going to finish with f inverse. So f inverse is this x minus 9 over 4. If you wanted to separate it and say it's 1/4 x minus 9/4, feel free to do so, but I am perfectly good with that answer that I have there in the box. Okay, if you want to, maybe pause the video and try these other two, go ahead. I'm going to keep working, and if you did pause, you can pick up where we left off here. Okay, so the next one, I've got g of x equals x plus 3 over 5. Again, replace f of x, g of x. That's just another name for y. Then you switch the x and the y. So instead of y equals, it becomes x equals. Instead of x over 3, it becomes y over 3 plus 5. You switch the x and the y. You use the definition of the inverse. Now we solve for y. So I subtract 5. So I get x minus 5 is y over 3. And then lastly, to get rid of the 3, I multiply both sides by 3. So I get 3x minus 15 is y. Or in other words, since we started with g, I get g inverse of x equaling 3x minus 15. Okay, let's do a couple of, we'll do one more last one here, d. Then we'll start to get into the creepy ones, because it's not always this easy. The ones we've been doing so far are kind of easier because they're linear. When you have like a line is a 1-to-1 function. It passes the horizontal line test. It'll also, no vertical line will cross it in more than one place, so it passes the vertical line test also. When you start getting into a variety of curves, they may not be 1-to-1, and that's going to pose some problems. So part D, I got fx equals 6 minus 5x over 7. F of x is another way to say y. Now we find the inverse. You switch x and y, so it becomes x equals 6 minus 5y over 7. And now we look to solve for y. So first thing I'm going to do, if that fraction bothers you, it's about to be made easier. I'm going to multiply both sides by 7 to get rid of that off the bottom. Then I'm going to subtract 6. So I get 7x minus 6 is negative 5y. I divide by negative 5, and I basically get that f, oops, that's a negative 5. I get f inverse of x is 7x minus 6 over negative 5. I know some mathematicians get a little picky about it, and they don't want you to have the negative on the bottom, so they'll write it like this. And if you change the sign of the bottom, you have to change the sign of everything on top. Personally, I don't really have a preference. Both of those answers are acceptable. Okay, so there's a little thing I put together just in hope that it might help you. So basic idea, when you're dealing with a function or some rule for f of x, whatever it might be, you take your input, your x, your domain, whatever you want to call it, you plug it into the function. And then you get something out, that's your output, it's your range, it's your y. Now, when you do an inverse, the rule is basically what goes in, well, the output does, so the y value goes in to the inverse, and it should take you back to your input or your x. So again, like if I put in the value 1 here, if I find f of 1, let's say this gives me a value of like 3. So here, I would take the value 3, plug it in, and I'd be right back to the 1 I started with. That's kind of the idea. Okay. Now let's find the inverse of x squared. Now, you might think, this is no big deal. I got this, no problem. So, okay. So I do what we've shown. I take and change the f of x to y. I switch x and y. I square root both sides. And I get y equals square root of x, or I get f inverse is root x. Not necessarily. Let's take ourselves a little look at that. So here's what we had. We had f of x is this, and we got f inverse equals root x. Let me show you why that's not such a great thing. If I were to graph my function right here, hold that thought. I lost where my location was. Here we go. So here is my parent function, f of x equals x squared. Remember what I told you about when we were doing lines before? Passes vertical line test, passes horizontal line test. It's a one-to-one function. It's pretty kind of straightforward as to what you do. Here, while this does in fact pass the vertical line test, it's not a one-to-one function. It wouldn't pass the horizontal line test because what would happen is that a horizontal line would intersect it in more than one point. So that's going to end up being kind of problematic for us. So I'm going to show you how we deal with that. So let's go back and do our graph again. Here's your parabola here. So the idea I need you to know is that when we're doing inverses, if your function is not one-to-one, there's going to be some problems. And let me show you how that's going to look. Now, again, looking at your parent functions, remember we did the graphs of the parent functions for your basic functions. So I'm going to go ahead and draw the square root function. And this may not be a perfect graph, but it looks something like this. And I'm going to also draw, I'm going to draw it as a dotted line. The line y equals x. And what I'm seeing here is that I don't see a reflection over here that's the same over there. So in that instance, here's what I'm going to do. I'm going to restrict the domain. I'm going to cut off part of it. So basically what I'm going to do is I'm going to say that if f of x is x squared, then f inverse of x is root x, where, and what was the domain restriction I did? Again, we had this piece over here, and I just said, nope, you don't play into the equation. We only kept this part, and now it is symmetric about that line. So if you cut out this piece right here, then we do get that y equals x cutting it in half or being symmetric. So what did I keep for the parabola? From 0 on. So where x is greater than or equal to 0. So when your function is not one-to-one, like a parabola, you need to do a domain restriction. That's something that's kind of important for you to know. And I'm going to show you some calculator screenshots of this too. Again, if I draw, and again, this is a better graph than the one I drew, but if we draw your parent function y equals x squared and the inverse function y equals x, no way does this line cut it in half. But if we restrict the domain, then I do get that this parent function line y equals x does cut it into two things that are mirror images across the x-axis, across the line y equals x. Okay. Let's even take another little look at it. So let's say I don't do a domain restriction. Again, just a sheer looking at points. Again, this would be f. This would be f inverse. F has 2, 4. F inverse has 4, 2. Sounds good so far. But what if I take the negative 2, 4? Do I contain the point 4, negative 2? I do not. That's the problem. So that tells me I need to restrict the domain. So when I restrict the domain, that means none of this garbage is existent. So I have 2, 4. I have 4, 2. I have basically solved that whole problem of the not being one-to-one by doing the domain restriction. Okay, now doing a problem like this, here's what I'm going to actually do on it. I'm going to start by graphing this parent of x. Now remember, this is a basic parabola. This is your transformation, your k, your vertical shift, which means it's going to go up 3. So my graph of g of x, 1, 2, 3, looks something like this. Again, question I ask myself, is this a one-to-one function? Well, would it pass the vertical line test? Sure. Would it pass the horizontal line test? Not feeling so good about that, so it's not a one-to-one function. So before I get crazy here and start trying to find my inverse, I'm going to restrict the domain. So my domain, and I'm going to write this like a little subscript here. My domain of g of x is, well, basically I want to cut off the left side of it. I'm only going to keep from 0 to infinity. So I'm going to say that x has got to be greater than or equal to 0. Now, we may also have a domain for g inverse as well. We'll get to that here in a minute. So we've restricted the domain. So now if I take this piece off right here, we now have a one-to-one function which does have an inverse. Now, here's g of x. So g of x is x squared plus 3. We replace the g of x with y. To find the inverse, we switch x and y. Oops, so that would be not y squared, but x equals y squared plus 3. We subtract the 3, and I get x minus 3 is y squared, and I square root both sides, and I get y equals square root x minus 3. So I get that g inverse is the square root of x minus 3. Now, transformations. Remember we had y equals a times f of x minus h plus k. So our little x minus 3 is inside, so this is going to go 3 units to the right. And let me do that in a different color here. So it's going to go 1, 2, 3 units to the right. And that's our square root function. Now, that is my g inverse. And again, if I draw that linear parent function, the line y equals x, does it cut it into 2 equal halves? It sure does. But is g of x defined, or g inverse defined for all values? Well, no, it starts here at 3 and it goes on. So the domain for g inverse is that x is greater than or equal to 3. So this is what I want your answers to look like. Does g of x need any restrictions to make it one-to-one? If so, list them. Find your inverse, and then does your inverse need any restrictions? Remember we talked about this in the last lesson, the operations. When I have like an x minus 3, something like that. Remember that when you have a square root, we don't want to take the square root of a negative. That's not good for us. That gives us an imaginary. So we take the inside, make it greater than or equal to 0. You add 3, and you get your domain restriction for g inverse. Okay, let's take another shot here. Now, I would like to restrict the domain on this, but here's what I don't want to do. I don't want to go ahead and like pick some points like -3, -2, 1, 0, -1, 0, 1, 2, 3, and like plug in and find points. I don't want to graph it that way. So you'll see why it is that I taught you, or that I kind of refreshed your memory on all those parent functions before we started. They're going to play in a very large role here into this problem. So first thing I'm going to do is I'm going to change the f of x to y. And I'm going to write this in transformation form. So I want to turn this into something like this. Y equals a times f of x minus h plus k. So to do that, I'm going to factor. X squared is x times x. Can you think of any factors or multiples of 25? Well, 25 is either 1 and 25 multiplied or 5 and 5 multiplied. Which of those will add up to 10? I'm feeling pretty good about the 5 and the 5. And since both of these signs are positive, so are these. So now I get an equation, y equals x plus 5 times x plus 5, or x plus 5 squared. So now we have it written in that good form here, that vertex form, or transformation form, I've heard it called as well, that's going to let me graph it. So looking at this graph, again, what I have is an x plus 5 in parentheses, so it's like the inside here. So I have a horizontal shift. So this is going to go to the right, or I'm sorry, to the left 5 units. So it goes 1, 2, 3, 4, 5 to the left. There's my new vertex. And then it's a positive x squared, and it's a parabola, so it's going to look something like that. There is my f of x. Again, take this, convert it to this vertex form, and life's going to be good. Now again, there's going to be 3 things I'm looking for here. Like number 1, I guess something I want to consider is this a one-to-one function? I'm not feeling it, so we're going to make it one-to-one, okay? So let me erase. I think I'm going to erase here. Okay, so let's try this again. Again, my drawing is not to scale. Oh, that's a really, I think my other parabola was better. So again, doesn't pass the horizontal line test, so I'm going to have to do a domain restriction on the original function f of x to make it one-to-one. The restriction I'm going to do is I'm just going to cut off that left-hand part there. So what did I keep? I kept from 5 on for the x value. So my domain of f is going to be that x is greater than or equal to -5. That is one part of my answer. I am probably also going to have to restrict the domain of f inverse, either to make it one-to-one or even to make it defined, and then we can find f inverse. So when they're not one-to-one, there's going to be 3 things you're going to include in your answer. So now we got the domain of f, let's go ahead and find f inverse. So we switch the y and the x so we can do the inverse. Then we square root. So I get x equals y plus 5. I subtract the 5. Now here's the thing. The 5 is not inside of the square root. The x is. So I'm going to write it as root x minus 5. So my parent function, or let's do this. So I'm going to rewrite that then as f inverse equals root x minus 5, which is going to look something like this. Again, the minus 5 is not inside of the square root with it, so it's not a horizontal shift, but rather a vertical shift of down 5. And then the graph of the square root function does something like that. That's f inverse. And if I draw the linear parent function, y equals x, does it cut it in half? Yeah, if you draw better than I do. However, let's take a look here. Did my graph of f inverse, does it go all the way back there? Or in this case, no, it doesn't. Where does it start? Its domain is from 0 on. So this domain we used because basically it made f of x one-to-one. This domain I did because it makes f inverse defined. Or in other words, by putting in only numbers from 0 and beyond, it makes it so that this square root is not negative, which would give us the imaginaries. I know this is a little to wrap your head around, but let's play with a couple other ones, okay? Over here, I got f of x equals x plus 3 minus 2. Again, look at your transformation form, your vertex form. Let me erase that here. Minus 2, or plus k would probably be better. And what do I have? Well, that inside is telling me I'm going 3 to the left. This right here, the minus 2 at the end, tells me I'm going 2 down. So let me go ahead and make my graph over here. So instead of starting at 0, 0, I go 1, 2, 3 to the left, and 2 down. And that is the starting point of my function. Now again, it is the square root function, so it's going to go, I don't know, something like that. That's going to be my f. Now we look at our domain. Is my function defined at all values? Well, no, it starts right here. There's really nothing going on back there. So it starts at -3, so, and goes onward, so it's x is greater than or equal to -3. Now we switch f of x and call it y. We switch the x and the y to do the inverse. We add 2. So I get x plus 2 equals root y plus 3. We want to get rid of the square root, so we square both sides. Now, here's something you can do. I wouldn't recommend it because it'll make the graphing harder. I know that when I square that, it's going to give me x plus 2 squared, which is x plus 2 times x plus 2. And if you FOIL that out, you get x squared plus 4x plus 4. While it is correct to do that, it's going to make it an awful lot harder to graph. So again, I want you to make sure that when you're doing these, that it is in that transformation or vertex form. So I'm going to just say then, that gives me x plus 2 squared equals y plus 3. Then when I subtract 3, I get y equals x plus 2 squared minus 3. This is in this transformation form. So this is going to be a parabola, and it is going 2 units to the left and 3 down based on this and this. So again, I'm going to need to restrict the domain for f inverse. And then I have f inverse, which we just found was x plus 2 quantity squared minus 3. Okay, again, let me select a little different color here. To do this, let's go with that blue. So again, we said we're going to go 2 left and 1, 2, 3 up. And there is my f inverse. Again, is my f inverse 1-to-1? No. So I'm going to cut off that part and only keep from where x equals 2 and beyond. So my domain for f inverse is, no, I did something amazingly stupid. Let's try this again. Maybe I want to try 2 left and 1, 2, 3 down. That looks better. And again, I'm only going to keep that right side here because I want to keep it to be 1-to-1, and then my line y equals x right down the middle. So what is my domain? I kept from -2 on to infinity. Hopefully this is starting to make a little bit of sense. Okay, Number 6, use composition to show that f and g are inverse functions. Now, when we're talking about this composition, remember this is where we talked about like f of g of x, or we'd take like g of f of x. Remember how we said that these two functions are not commutative? In other words, the order in which you do them matters. Whether you go from the inside or outside first, it matters. What I'm telling you is when they are inverse functions, it actually is commutative. If two functions are inverses, then what you're going to get is that here, this f of g of x will equal g of f of x. And what's more, not only will these two functions be equal, but they will equal x. So what I'm trying to say is that when you're doing composite functions, that is the only time that composition is commutative, where it should be the same whether you go f of g or g of f. So let's look at our two equations. I have f of x is x squared minus 3. And I have g of x, which was, let me go back here, x plus 3 square root. Now, again, are they inverses? I can kind of just give myself a little visual check right here, in that this is right here is a parabola that goes down 3, 1, 2, 3, something like that. Since we're talking about inverses, it's not 1 to 1 there, so I only keep the right half. And the other one is x plus 3 square root, so it's 1, 2, 3 to the left. We draw the square root, and they appear to be inverses based on just the graph and appearing to be symmetric across y equals x. That is not proof. So here's what I want you to do. Rather than saying, okay, let's call this y, and that's x squared minus 3, let's switch x and y, rather than actually finding the inverse of f and seeing if it does equal this, I want to actually use composition to show that f of g, g of f are the same and they equal f. So let's first find f of g of x. Well, that's going to be f of g of x is root x plus 3. Now, f tells me to take something squared and subtract 3. That something I'm going to square is x plus 3, giving me x plus 3 minus 3, which cancels to make x. I'm feeling pretty good about this so far. F of g of x gave me x, just like we said it would. Now, this also has to be true. We got to find g of f and make sure that's true as well. So g of f means I'm taking g of, and I'm plugging in the f of x. G says take the square root of something plus 3. What's the something? It's the function f of x, which makes those reduce. That makes x, and we're good. So I would say something like this. So since f of g of x was the same as g of f of x, and since they both equaled x, then f and g are inverses. Kind of some cool stuff. Now, for f of x equals 3x plus 7, find f of f inverse of 3. Now, here's the one thing I know. Oh my God, I got to do all these domain restrictions again. No, this is a y equals mx plus b. It's like a, you see it have an intercept at 7 and like rise over run 3. It'd look something like this. So, is it 1 to 1? Does it pass the horizontal and the vertical? Yes and yes to both. So, since this f of x is 1 to 1, I don't have to worry about restricting the domain. Basically, any line, I don't have to worry about restricting the domain. You know, maybe unless it's a vertical line, we have an undefined slope that may cause some problems. But so let's go ahead and find the inverse. So I'm going to replace this f of x with y equals 3x plus 7. I subtract the 7. And then I divide by 3. So I get, oh, no, I didn't switch the x and the y. Let's try that again. So I get y equals x minus 7 over 3. Or in other words, here's f of x. We got f of inverse of x to be x minus 7 over 3, which is also a line. It's the same as saying 1/3 x minus 7/3. So it is also a line. It is also 1 to 1. So no domain restrictions are needed. So what I'm asking you to find is f of f inverse of 103. And again, with composite functions, you start on the inside and work your way out. So let's first find f inverse of 103. Here's my f inverse. It says to take something, subtract 7, and divide it by 3. That something is going to be the number 103. 103 minus 7, I believe, is 96 over 3, which is 32. And if we plug that into f, f says take 3 times something and add 7. 3 times 32 is 96 plus 7. 103. Yay. Easy enough to do. It's easier than that. Honestly, you didn't have to do any of this whatsoever. I could have saved you a boatload of time because look what happened. What did we do? We found f inverse. We plugged into f inverse. Whatever we got from there, we plugged into f. What did we get as an answer? Well, we got 103. Have you seen 103 before? Hey, wait a minute. That's the same thing I started with. Is that like some weird coincidence thing? And the answer to that is no. I can tell you, when I see if I have two functions that are inverses, whatever f does, f inverse undoes. So those basically cancel, leaving you with 103. So if I wanted to do something like this, let me erase here. So I could give you some function g of x. I don't even have to know what g of x is. So let's do this. So let's say g of x equals blah, blah, blah. I don't care. What is g of g inverse of like 17 pi? Say, well, how am I supposed to do this? I don't know what g is. I don't know what g inverse is. I don't have to know. If they're inverses, they're defined. They're both 1 to 1. G cancels g inverse. 17 pi it is. So little shortcut that may save you some time and effort. Okay. Again, I have a graph here. Negative x plus 7. That is a line of the form y equals mx plus b. Has a y-intercept at 7 and a slope of 1. Looks something like this. Here's my f. So it is 1 to 1. It passes vertical line test. It passes horizontal. So let's go ahead and find our inverse. So we switch x and y. We subtract 7. So x minus 7 is negative y. You can either multiply both sides or divide everything by negative 1, which gives me y equals, actually, you know what, I like the idea of dividing or of multiplying by negative 1 better here, but certainly it would have worked the other way as well. So I'm going to multiply this by negative 1. And I'm going to multiply this by negative 1. So that's going to turn that into a y, that into a negative x plus 7. So what do I get? I get f inverse of x is negative x plus, whoa, dude, that's like creepy. It's the same thing. So like the function and the inverse are the same thing? Is that even a thing? Can that be? Well, let's look at the original graph of f. If I were to draw the parent function, y equals x, it does. Basically, the original function right here itself gets cut in half across the line y equals x. It has symmetry across it. So, yeah, it is possible for f inverse and f to be the same function. So some functions can be their own inverses. It's a little creepy, but possible. Okay, let's do this one again. Here's f of x. I want you to find f of f inverse of 103. If the first thing you're thinking about doing is, okay, let me call this y equals 3x plus 7. Let me switch the x and the y. No, don't do it. It's much easier than that. Whatever f does, f inverse cancels. You end up with the same thing you started with. That's kind of cool. You say, no, I want to do it the other way. I want to actually find out what f inverse is. And in this case, f inverse would be, I think, x minus 7 over 3, I think is what it is. And you could plug in and get that. The reason I say I don't want to do that is because of a problem like this. You want to go ahead and find what g inverse is of this function. You go right ahead. You can deal with trig and all these awful fractions and irrational numbers and all that. You have a blast. For me, g inverse does something, g undoes it. I end up right back where I started with. So, hope that kind of helps you and that this kind of makes a little bit of sense. So, that's a wrap, folks.